What I think we should do is we should multiply that by something that converts it to just exponentials or to just minus exponentials. Since we're thinking about x going to infinity, if we could get e to the minus x, fun fact, the limit as x goes to infinity of e to the minus x, that's 0, right? Because this is really 1 over e to the x, right? And as x goes to infinity, this gets huge. 1 over something huge is tiny, which is 0. So how can I convert everything here to e to the minus x's? Well, I could multiply this by e to the minus x over e to the minus x. If I do that, then what will we have? 1, right? This times that is 1. They cancel. E to the minus 2x, yeah. These guys multiply to give me 1. These guys give me plus e to the minus 2x, right? But another way to look at it is e to the minus x is the reciprocal of e to the x, which, by the way, is hilarious according to my son. But just the reciprocal part. So with this little bit of algebra in hand, we now have an expression where we've got stuff that goes to 0 and other things which stay 1, right? So we can just take that limit using limit laws. We've got 1 minus 0 over 1 plus 0. So 1. So graphical approach, algebraic approach, all right? Before this, the other board was basically common sense approach. Just think about what happens to the function's formula as x goes to infinity or minus infinity, all right? So I cannot, nor do you want me to tell you all of the examples in the notes, all right? So like the examples in the notes are legion. And I'm talking about page, please read page 228, 229, 230, and 231. Basically please read through pages 229 through 235 or so. This should be 36. I'll get to it eventually. 237. So it would be good for you just read my notes, page 229 to 237. All right? Because in these notes, I give further examples like I've already given, and I show you how we could use algebra to solve certain limits. All right? And after you read those notes, if you have any questions about them, we can talk about it in class, all right? But what I'm going to do with the remaining 10 minutes or so here is I'm going to talk about what comes after that, which is more interesting and a little bit more, well, really quite surprising. And this is what's known as L'Hopital's rule. L'Hopital's rule gives us another tool for unraveling limits of indeterminate form. So if we had limits of type 0 over 0, what did we do up to this point? What did you do on test 1 if you had a limit of type 0 over 0? What happened? We had to do algebra, right? Deal with it, right? Exactly. Like just hand-to-hand combat with algebra, basically, right? So what's L'Hopital's rule says something really beautiful. And the spelling on L'Hopital's rule is debatable, and I don't really care to debate it. But I'm just going to say this Some people say Le Hospital rule. It's a translation from French, and then it's got translated different times, different ways, and I don't care. So if you want to call it Lhop, the rule if you want. This is one of those things where it's not actually due to this guy. I think this was discovered by, I want to say like Lagrange, but L'Hopital wrote one of the first very popular, widely used calculus texts, and so the rule goes to his name. But I don't think he actually is the one who found it. Perhaps he popularized it with his book. But here it is. If the limit of f equals 0 and the limit of g equals to 0, then the limit of f over g is equal to the limit of f prime over g prime. If the limit of f is plus or minus infinity and the limit of g is plus or minus infinity, then the limit of the quotient of f over g is equal to the limit of f prime over g prime. And this statement, it holds whether or not the limits on the far right of these expressions exist or not. So it's meant to include the cases that the limits are divergent. So let me show you an example which is completely sort of a most hypocritical possible example in some sense to give of L'Hopital's rule, but the reason it's hypocritical is probably something you've forgotten, but here it is. The limit as x goes to 0 of sine of x over x so what happens to the limit of sine as x goes to 0? Limit of sine as x goes to 0 is 0. Sine of 0 is 0. What's the limit of x as x goes to 0? 0, right? So this one is type 0 over 0. This one is type infinity over infinity, you know? And so here's my notation, guys. And I can't, I'm not enough of an expert in LaTeX to make this appear in my notes. I need to hire like a black belt in LaTeX to make this appear here. What this notation means is I'm applying L'Hopital's rule, type 0 over 0, in this step. So you'll see this in my handwritten solutions. You won't see it in my notes because I don't know how to make it appear in the typesetting. But here we go. You got cosine of x over 1. And see what happened? What's the limit of cosine as x goes to 0? It's cosine of 0, which is I heard a 1. I heard a 0. Which one do you guys want to stick with? 1. 1 is a good choice. Yeah, so cosine of 0 is 1. So the answer is 1. Now, the reason I say that this example is a little bit hypocritical on my part is if you really search your soul, you'll remember that when we found the derivative of the sine, we needed to know that the limit of sine h over h was 1. So it's somewhat circular reasoning to use differentiation to do the limit. Anyway, this is a fine calculation. It's just anyway. Example 2. Limit as x goes to infinity of like x e to the minus x. Now, at first glance, this is not a quotient, right? Notice that L'Hopital's rule tells us how to unravel indeterminate quotients, either type 0 over 0 or type infinity over infinity. So the first thing I need to do is to convert this to a quotient. So what can I do? You guys tell me the algebra here. I'm going to leave x upstairs, mind its own business. And what is e to the minus x equal to? It is equal to 1 over e to the x, right? So I can rewrite this as x over e to the x. And now, what happens as x goes to infinity? Well, as x goes to infinity, certainly x goes to infinity, right? The numerator goes to infinity. What happens to the denominator? As x goes to infinity, the exponential goes to, no, positive infinity, positive infinity. So this is type infinity over infinity, which means we're just in luck. We can apply L'Hopital's rule. Woohoo! So equals L'Hopital, type infinity over infinity. And what we got? By the way, notice that L'Hopital's rule doesn't say you have to do quotient rule. No, it says every calculus student's dream that when you differentiate the quotient, you just differentiate the numerator and differentiate the denominator, right? Please do not misapply this to just plain differentiation. That's a different calculation altogether. When we have a quotient, we're just differentiating. We have to do quotient rule, right? This is the limit. We're applying L'Hopital's rule. Derivative of x, 1. Derivative of e to the x. Just e to the x again, right? And can you guys tell me how to calculate this limit? So if you're not confident yet about how to calculate the limit we just came to, that's part of why I've asked you to read 229 to 237. It's all about those kinds of limits, all right? But this should be what? So what happens as x goes to infinity, e to the x goes to infinity, right? So we're looking at 1 over something huge, which is 0, right? Now, let me ask you again. Think back to how you had to calculate limits at the start of this course on test 1. Is this easier or harder than that? I mean, I would argue that this is considerably easier where this method applies. And so, like, as you leave this course and you're, thinking about calculating limits of functions, this is one of those tools I'd like you to leave the course with, is L'Hopital's rule. It's very helpful for calculating certain kinds of limits. Also, this is not something I'm going to prove. The proof of L'Hopital's rule is like just a monstrosity. It has many, many cases. It's not particularly interesting. I'm just going to state it, and we'll use it. So, anyway, thanks, guys. I will see you Wednesday, I hope. If you see any of your missing classmates, tell them we miss them.